Hi guys, I'm Eric, and today, we are going to be continuing learning number theory. The last lesson we ended with 3 prime theorems. I guess you can call them. The last one is n to the second power minus 1. These kind of primes. Now we figured out that we hadn't quite figured out how to prove are there infinite or finite numbers of these kinds of primes. So now let's change that number to a to the nth power minus 1 with n greater or equal to 2. And of course, to start off, we are going to have a list. Just like that. And first we find that if a is an odd number, then a to the nth power is definitely an odd number. Odd numbers times odd numbers are odd numbers, times odd numbers are still odd numbers, you name it. And an odd number minus 1, which is also an odd number. I don't know how many times I said odd. It's gotta be an even number, which means it can't be prime. And also, we find that seemingly a to the nth power minus 1 can always be divided by a minus 1. And the reason for that is a to the nth power minus 1 can be factored out into a minus 1 times a to the n minus 1's power plus a to the n minus 2's power. You name it all the way to 1. And the reason for that is, well, we look at this and we find that we can do something. We look at it and we get interested, and we find that we can get it into x to the nth power plus x to the n minus 1's power plus all the way to x. Forgot these 3 dots. And then you minus out the extra parts. I'm running out of space here, so I won't write that much, plus 1, because you gotta keep a minus 1. And we find that we can factor out 1x, because else if we factor out 2x, this x will get lonely. Plus x to the minus the second power all the way to 1, since we had factored out the x. And of course, we're going to keep this unscathed because it's a spectator ion. After that, we find that this and this are the same terms. So we have it. Well, I was using x all the time. Well, just think that x and a are the same thing. Oops. All the way to 1. We have found that a to the nth power minus 1 will always be divisible by a minus 1, or x minus 1 if you want to call it that. So, yeah, we found this ages earlier. And we had also found this, that it can always be divisible by x minus 1. And a minus 1. Oh my gosh. And if we want a to the nth power minus 1 to be a prime, then of course a minus 1 must be 1. Which means that, well, a is 2. So a must be equal to 2. So now it's no longer a to the nth power minus 1. It's 2 to the nth power minus 1. And I'm going to risk my life skipping to the next page. Yes, so when a equals 2, it is the only way that this will actually work out. And of course, we've got a totally new list, And this time is 2 to the nth power minus 1 that we're observing. And we find that, distressingly, a lot of these numbers are not prime at all. So, what can we gather from these data? So we find that 1n is even. Then 2 to the nth power minus 1 will always be divisible by, well, 2 to the 2nd power minus 1, which is, we can just calculate it in our mind without using a paper and pen. We get 3. So it must be divisible by 3, and we can just, yeah, we found that. And when n is, oh my gosh, is that an m or an n? Or a mutant n? When n is a multiple, I'm just going to write MUL. Don't write MUL in your math class, you know. If n is the multiple of 3, I'm just getting very lazy right here. 2 to the 3rd power minus 1, which is 7, and we'll always divide 2 to the nth power plus minus 1. And you didn't guess that I'm going to write an O there, but you guessed it. If it's a multiple of 5, then 2 to the 5th power minus 1, which is, oh my gosh, I almost said 25. How did that come into my mind? It must be divisible by 31. And unfortunately, there is only one example over here. Yeah, lonely. So we can just make a very bold move, and we'll state that if n is divisible by m, and we've got to write this backwards, or yes, I think I've got to write that backwards. Should I? Oh, never mind. Then, not a, oh my gosh, to the nth power minus 1 will be divisible by 2 to the mth power minus 1. And once we make that observation, it's quite easy to prove. And it might not seem easy at all, but I promise you, it'll only take a few seconds. So, n is equal to mk, because m is a factor of n, and so 2 to the nth power minus 1, of course, over here, it can be written as 2 to the mkth power minus 1, which is 2 to the mth power, brackets, okay, not brackets, parentheses, minus 1. Well, just like that, we can substitute this into this equation from ages ago. And we have, I'm going to rewrite it for convenience. I'm just gotta fix that m. I don't know why. So it's basically the same as 2 to the nth power, but in this case 2 becomes 2 to the nth power and becomes k. So that's basically the only change. And if you get that over in your head, we have this. And of course all that stuff from before. So yeah, we have yet another problem. Yay. So 2 to the nth power minus 1 must equal 1 as well for it to be a prime, which means that n must be prime, or else 2 to the nth power minus 1 will be composite. And actually, there might be a chance of it being composite even while n is prime. But in this little list, we can gather that 2, 3, 5, 7 are all primes. And so we can get this proposition, which is basically the two long sentences that we had proven ages ago. And we find that this is not a common prime, and we had just stumbled into Mersenne's prime. Oh my gosh, I remember the Chinese name, and it's something like Mason, so I always almost say Mason's prime. Well, in fact, it is Mersenne's prime. I heavily suspect that he changed it to Mersenne because of some religious reasons, since he is a godfather. But who cares? So he said in 1644, I'm going to note his name down. Hopefully I don't misspell it. Yes, I think that's it. In 1644, he said that if 2 to the p's power minus 1 is going to be a prime, then p is either 2 or 3 or 5 or 7 or 13 or 17 or 19 or 31 or 67 or 127 or 257. And if you want to write that list down, go ahead. I'm too lazy. And we actually find he makes 5 mistakes right here. He shouldn't have included 67 and 257, and instead he should have added 61, 89, and 1007. That's not smaller than 258. 107. Of course, we found that with a calculator, not by hand, because in the 17th century, finding this is already incredibly impressive. And right now, yes, today, there is a website called GIMS, or rather GI. Oh my goodness me. GIMPS, this website, it just, finds Merssenne's primes. And yeah, sure, finding those primes can be fun, but it might not be as fun as proving that there are infinite Mersenne's primes, which means that we end with a question: are there infinitely many Mersenne's primes? And I had just ran out of space. So there is a piece of poetry involved that I completely forgot how to read it, but never mind. So the question is, are there infinitely many Mersenne's primes? And just as n squared minus 1, we can't prove it. So we had just stumbled into Mersenne's primes and, whoa, just close that PPT. Anyways, that will be the end for today. Not the end of the world, the end for today.